Hello, I'm Mike McCulloch. So today I'd like to talk to you about a thruster that was experimented on for many years by James Woodward in California, called the sometimes the Mach Effect Thruster, or the Woodward Effect. So I'm going to talk about a particular version of this that was published in a STIFE conference in 2000 by Mahood. In 1999, he did the work, and he had a system that was set up a bit like this. So he had 40 plates of what's called PZT, or which is lead zirconium titanate, which you can't always buy in a corner shop. And he stacked these up as shown in this diagram. So the 40 of them, and about 2 centimeters high. And then he had a capacitor on top of them, and that was connected to a heavy plate. I think it was brass, but it was some kind of metal. And then he injected 140 watts of power into the PZT, which is a piezoelectric material. And whenever you energize it, it flexes, it vibrates, it moves. And he injected this energy at a frequency of 11 kilohertz. So very high frequency, and they observed in this experiment a thrust upwards towards the heavy plate of 50 micronewtons. Now, although I appreciate Woodward's experiments, I don't buy the theory that he proposed. That's no criticism of Woodward. It's just part of science, because his theory predicts that the thrust should have been as shown in this formula. So the frequency of the current applied cubed times the length of the contraption times the power input, which gives us 0.05 micronewtons instead of 50, so it's 1,000 times out. So does QI predict this system? Well, I guess you know that it does, otherwise I wouldn't be talking to you about it now. But with QI we can start from the basics. So I go back to, as usual, Heisenberg's uncertainty principle. So the uncertainty in position, delta P, times the uncertainty uncertainty momentum, delta P, times the uncertainty in position, delta X, is h bar over 2, where h bar is the reduced Planck's constant. And then we can say that the momentum is the integral of the force with respect to time, so as shown here. And also, instead of assuming that we have a quantum background h bar, we acknowledge the fact that we're pumping a lot of energy into this system. So the value of h bar is going to be the energy we put in times the time it stays in there. So I'm going to call that dt. So what we get after that is delta F is E over 2 dx, because various things cancel. And then the energy is just the power we put in times the time that power stays inside the system without dissipating as heat or whatever it is. So we get dF is P dt divided by 2 dx. And then we can work out the time that the energy stays within the system based on what's called the quality factor of the system, or the Q factor. And you can calculate that as QL over C. So we put that in. So this is the force we would expect to get, but what I'd like to do now is just show that there's an asymmetry here, because although this force is being applied by unradiation, there's a heavy plate above which is going to damp that completely, and there's not much below which is not going to damp anything. So there's going to be an asymmetry in this system. There's going to be a lot of unradiation force from below pushing up, and not so much pushing from above pushing down, because of this brass plate which is absorbing all the under waves. So they will come from below but not above. So we should get an uplift. So we can calculate this by taking the difference. So okay, we write it like this. So we've got PQL over 2C times a factor which is 1 over theta. Now theta is the distance to the cosmic horizon, so that just means that this term is going to be very small, and this is the term that refers to the to below the system. There's no barrier there, so the system can effectively see to the cosmic edge. But the second term will be half the distance to the brass plate, because the brass plate is the horizon that is above, and that's damping the under waves from above. So that's what that equation means. We can cancel the first term because theta is something like 10 to the 26, is 8.8 times 10 to the 26 meters. So that goes. So we just get the second term, and then we get that the force we're going to see is going to be PQ over C. So the power we put in, the quality factor of the system divided by the speed of light. And if we put the values in, so 145 for the power, that's in watts. The quality factor, now this I've taken from a similar experiment as 60, but I've also calculated it from a more complex method and I got 53, so I'm just going to put in 60 here. That's a little bit uncertain, but it's going to be something like that. And then divided by the speed of light, which is 3 times 10 to the 8. And then we get about 29 micronewtons, which isn't too far from the 50 micronewtons that we had, and given all the uncertainties in the Q factor and things like that, and also perhaps in the speed of light, because that will vary within the material, it's close enough to the observation that this is interesting. So it seems that quantized inertia does predict this particular Woodward thruster, the Mahood 1999, and you can see the paper that he wrote on it. And this also illustrates the kind of point that quantized inertia predicts thrust. Every time you put energy into a small area, you concentrate energy, and you make the structure asymmetric. Whenever you do that, you get a thrust towards the part of the structure that is more dense. Okay, so I hope you've enjoyed this short. Please do subscribe to my Patreon, become a member on YouTube and my channel if you wish, and I look forward to speaking to you next time. Goodbye.